Okay, so this is from the 2018 paper to prove using induction, essentially prove de Moivre's theorem using induction. So the first step you have to take is to prove that the statement is true for n equal to 1. So to do that, you get cos theta plus I sine theta to the power of 1 equals cos of 1 theta plus I sine 1 theta. So this raised to the power of 1 is just cos theta plus I sine theta, and this is the same, cos theta plus I sine theta. So that's true. Step 2 then is to assume it's true for n equal to k. So that makes it cos theta plus I sine theta to the power of k equals the cos of k theta plus I sine k theta. That's our assumption. Then we have to prove that it's true for n equals to k plus 1. So that gives us the cos of theta plus I sine theta to the power of k plus 1, and that should equal the cos of k plus 1 theta plus I sine k plus 1 theta. Okay, so what we're going to do now is we're going to manipulate the left hand side and try and make it equal this right hand side. So the first thing you deal with is the powers. So it's cos theta plus I sine theta to the power of k multiplied by cos theta plus I sine theta to the power of 1. So that's splitting up the plus into a multiplication. This part here, we're going to use the assumption to change that. So cos theta plus I sine theta to the power of k can be changed into this. So we have the cos of k theta plus I sine k theta multiplied by the cos of theta plus I sine theta. And we're going to try and manipulate this to turn it into this thing here, this cos k plus 1 theta plus I sine k plus 1 theta. So we're going to multiply this out. So first term, second bracket, so that will give us cos k theta cos theta, and this would be I cos k theta sine theta. Then this by this would give us I sine k theta cos theta, and then this one by this one, so the I by the I is an I squared, which is minus 1, and then we would have sine k theta sine theta. So I'm going to gather them then, the reals together and the imaginaries together. So the reals are cos k theta cos theta, and the other real is over here, minus sine k theta sine theta. The imaginaries then are these two in the middle, so it's cos k theta sine theta plus sine k theta cos theta. Okay, so now to get from here, we're going to use two of these. So this is the first one, and I will explain why. So here we have cos cos minus sine sine, and here we have cos cos minus sine sine. So we can rewrite this thing here as this, the cos of a plus b, so it's the cos. And in this case, the first angle is k theta, and the second angle b is theta. So this entire thing here becomes the cos of k theta plus theta. Then we have plus I, and we're going to apply just a different one, but the same concept here. So I think it's this one. So let's have a look at this one. So this one is sine cos plus cos sine. Okay, so here it's in the wrong order, but because the multiplication doesn't matter, so we have sine cos, and then plus cos sine, and we have plus cos sine. Okay, so in this case, our A is the theta, and our B is the k theta. So we can write it as this, which is the sine of theta plus k theta. Okay, so then just to simplify it a little bit more, we get the cos, and I'm going to take the theta out as a common factor, and that leaves behind k plus 1. And then the same thing here, take the sine, and take the theta out as a common factor, and you're left with 1 plus k. So then tidy that up, and you get the cos of k plus 1 theta plus I sine k plus 1 theta, which if I go back up here, underlined, is what we were looking for. So that equals the right hand side, which means you've proved your theorem. So you just take your little learned off part for the end. So you take this part, proposition is true for n equal to k plus 1, provided it is true for n equal to k, but it is true for n equal to 1 and therefore true for all positive integers, or whatever version of that you've learned off. That's it.